So
We'll give it next Friday.
next Friday, this is going to be a survival prize. The people will still be alive. So I want to talk about the mathematics of trust and adversity and go into cryptography considerably deeper than Avi's lecture, which touched on many topics, and show that in fact not everything would follow, even if factorization were hard, and not even if P turns out to be not equal to NP, that there are various aspects of cryptography which are extremely important and at the same time also extremely subtle. Now, actually, this is applied mathematics, and we know that game theory, about which you will have a lecture by one of the world's greatest, Aumann, game theory deals with adversarial behavior, where in an economic system everybody is trying to maximize his or her return or gain. But game theory in general and mathematical economics doesn't deal with a paranoid world that exists in cryptography. And as somebody said in a slightly different context, the good cryptographer never sleeps well. And I'm going to tell you some of the reasons and some of the remedies that we prepare so that, that the cryptographer might sleep well. So the plan is to talk about secure encryption, and in that connection mention briefly whether NP problems are intractable, then enter into something that was not dealt with and which is of cardinal importance in cryptography, average case hard problems, and then talk about various attacks, sinister and underhanded attacks on cryptographic systems which come after we have secure encryption. And this is malleability and chosen ciphertext attacks. Then we'll talk, in this connection, we'll talk about protocols, which is another aspect of cryptography. And then, last but not least, I'll let you into the secret how to achieve everlasting secrecy. So, first of all, public key encryption. So that was already dealt with. We have Alice who wants to send a message to Bob so that somebody who is an eavesdropper will not know the contents of the message. So this is being encrypted. One of the major points about public key encryption is that there was, as was mentioned before, private key encryption. And that meant that every pair of participants, say in the internet, who want to have secure, in this case, secret communication, need a public key, a private key that is common to them. Now, let us assume that there are 10,000 participants in this network or in that system, which is, of course, paltry and very small by comparison to the actual number. Then you need 50 million pairs of keys. Because if I have a private key with him, then I can't have the same private key with him because he, Vitali, I mean, not only could, but certainly would listen. Okay. So if we want to linearize the number of keys, the brilliant idea of Diffie-Hellman was that there is some, or there are some mathematical functions which use every Bob, Harry, Alice, Carol, and so on in the system will have a public key which is published in a directory. And in addition, say Bob will have a private key. Alice, if she wants to send him a message, will look up his public key, encrypt the message by his public key, and that's the ciphertext. He, Bob, has the secret information, which enables him to decode. And under certain rather dubious complexity assumptions, or certainly unproven, nobody except the person who has the private key can encrypt the message. So that's his private secret key. It's not shared between these two. And now I'm going to show you a system akin to RSA, but easier to explain, and which has some additional complexity features. So we want to talk about factorization-based public key methods. And the method is the following. Bob, the one whom we saw there, prepares a private and a public key by choosing two primes, large primes, for technical reasons more or less of equal length, say two 500-bit primes. Now in that, it is essential that you have an efficient algorithm for testing primality, and that was provided by the randomized method. And then he creates two primes, multiplies these two. N is his public key, which is publicized. It's like in a telephone book. And his private secret is the pair P and Q. Now, the method of encryption is trivially simple. The messages are taken to be integers written in bits smaller than n. But let's say if we had two 500-bit numbers, then n has 1,000 bits, and the messages can be a block of 1,000 bits. If you have a longer message, then you divide it into blocks and so on. Obvious technology. The encryption by n, so that is what Alice is going to do. She is going to look up Bob's public key, which is the number n. Now in intelligence test, how to start it. Good. So she is going to look up his public key, namely the number n. She encrypts by squaring and taking mod n. Now, Bob, who has P and Q, and that can be proven, can calculate the square root of the cipher text. Now, there is a slight problem that there are 4 square roots, but there are nice ways, very nice ways of disambiguating it, invented by Blum, by Manuel Blum. This is technical as far as we are concerned. Now we can prove the following, that, and this is a localized theorem. It's a theorem about the specific number n, not about factorization in general. That if the algorithm AL decrypts EM in time t, so I'm not even saying polynomial or not, 5 seconds, half an hour. If it can decrypt this for epsilon, since m is smaller than n, so there are n possible messages, for epsilon n of the total possible messages, m smaller than n, then P and Q, the factorization for this specific number, can be found in expected time twice t over epsilon. So if he can decode 1% of the messages each in half an hour, each, not all of them together, each, of course not all of them together, because 1% of the enormous number is an enormous number. But if for each of 1%, he doesn't even know which, he can decode in half an hour, then he can break the key in 200 hours, expected time. So that very strongly bases the security of this encryption method on the tractability of factoring. Let me also, in preparation for the future, point out that we are really saying that if, in fact, it is difficult to find these factors of n in, let us say, 200 hours, then for 99% of the messages, so this is also an average case hardness for this space of messages relative to the fixed n. For 99% of the messages, it is difficult to decode. And that's quite important because there could be a situation where, in the worst case, it's difficult to decode. But for any message, and let's say for all messages which are legitimate pages in the English language, it is easy. Legitimate sentences in the English language, it is easy. But this shows that you have average case hardness. So now we come to the question, how hard is factoring? Because the method we spoke about before depends on the factorization being hard. So now factorization is not polynomial. This is not a theorem because this algorithm, the general number field sieve method, which was, yes, I have the names. This is more or less, in the paper they had the special, but then they had expansions on that, but essentially it goes back to 1990. Factors, general numbers, therefore it's called general, factors general numbers n in time exponential, c times log to the 1/3, that's what, of course, Avi had, times log to the power 2/3. It's not proven, it uses some heuristic assumptions, but it works. C, let me mention, is a crazy number like 64 over 7 to the power 1/17. That follows from the method, is very close to 2, is about 1.9. And I'll get back to that point. Think about C as 2. And that enabled to factor numbers of this size, general numbers, which are about 2 to the 46, way beyond 200 to the 2 to the 460, way beyond what Rivest, Shamir, and Edelman postulated as being safe key sizes in terms of the length. Way beyond. Now, let me point out right away that this looks a little bit arbitrary in a sense. Now, if, for example, somebody, by some kind of an insight, not even a far-reaching insight, reduces this C to 1, to say nothing about 1/2, but let's say reduces it to 1, this C appears here multiplicatively in the exponent. And that reduces the time into a square root of the previous time. And that is going to double the length of the numbers factorable. So there are fine points here. Well, it's going to increase. Maybe I'm done. Pardon me?
The 8th power of the number, which is log of 1/3.
Yeah.
The double C multiply log n by 8.
No. For the same ends, C, I mean, in your algorithm.
In the same amount of time, we factor a bigger number.
Yes, yes. And you say it could be.
So C is yeah. Then you
Okay.
multiply n by 8.
Okay, much longer numbers. I didn't work it out, thank you. So that's probably right. Yeah. So that shows you how a small advance here could have extremely far-reaching consequences. And that's a point that we ought to bear in mind. A point that we ought to bear in mind. Very seriously. Now I want to mention another very prevalent method, and I'm going to tie a little bit later also this method and its applications to Gromov's question about finding examples for. So the discrete log method was in a certain way suggested already by Diffie and Hellman in a different way, but they proposed using a finite abelian, let us say cyclic group. with Q elements. It is enough to have a group. We can't always maneuver it to be cyclic. It is enough to have a finite group which has very large cyclic factors in the obvious, or let's say elements of very high order. But to simplify, cyclic group of order Q. And G is a generator of G. So examples of that are the multiplicative group mod P. This is another group, maybe I shouldn't go into it, but this is a group where it's going to be easy to find generators. You create a prime P which is of the form 2Q plus 1, where Q is a prime. So practically it's very easy by use of the primality test whether this would depend on unproven assumptions about primes, of this form. And then you take here the set of squares. This is a subgroup of order Q, and Q is a prime, and therefore every element is a generator. And finally, and that is an extremely important group, you take EP, the elliptic curve. P is a prime, A and B are smaller than P, and you look at this equation, the Weierstrass equation, you look at all pairs, you really should consider it in the projective setting, but just to simplify here, you look at all pairs which solve this equation. I failed to mention here that we need to assume that the discriminant 4AQ plus 27B squared is not 0 mod P, of course. So these numbers can be made into a group by a fairly crazy operation, which has, however, a very clear geometric interpretation. The time being so late, etc., I'm going to spare you that. It can be made into a group. Now, this is not always a cyclic group. However, by some twists and turns, the number of elements in this group is, by a theorem of Hasse, between P minus 2 square root of P and P plus 2 square root of P. And in fact, in fact, by Deuring and other analysis, every number there is actually it's actually attained with the same, for the size of the group, if I vary over A and B, with about the same density. Now, whether there are primes there or not, this is again, and there is one prime, P itself, but this is a very bad guy for a reason that I'll describe in a moment. But again, using some unproven assumptions, we can get A's and B's for which this is a prime. The size of this can be computed by a polynomial algorithm due to Schuf. So that can be maneuvered, and we can get those cyclic groups. Now, how do we use discrete log for encryption? This was suggested by El Gamal and is extremely simple. It's extremely simple. G is a cyclic group of order Q, and little g is a generator. So if, for example, Q is a prime, every element is a generator. We needn't worry about whether it is or not. Otherwise, it's more complicated. Now, Bob, this Bob over there, is still active. He chooses a private key, x smaller than q, but a fairly large number. And his public key is going to be h, which is g to the x. Now, Alice, her messages are going to be viewed as elements of G. So by some coding, or if we are talking about the residues mod P, they are essentially naturally already strings of bits. It's more complicated for the elliptic curve, because there the elements are more complicated. But it can be done. And the encryption based on the generator G and the public key H, this is what Alice does. She simply takes G to the Y, where she chooses Y randomly, H to the Y times M in the group. So either as residues mod mod P, or in the elliptic curve notion there, you actually write it additively, but it doesn't matter. Now, how do you decrypt? Notice that g to the y times x, x is known to Bob. He chose it, and he produced h as g to the x. G to the y to the power x is h to the y. So all he takes is the first component, raises it to his private x. He gets this. He divides it out in the group operation. He has m. Notice, by the way, that there are many encryptions for the same element, whereas that was not the case in the square method or RSA method, as given, the basic. So that's the encryption. Now, for that to be safe, again, I'm glossing over a few points here, but certainly if you can calculate the discrete log, what is now the discrete log? Keeping the same group in mind, given u, which is g to the x, then by some twist of language, we call the log of u to the base g is x. Of course, taken smaller than q. Now, it turns out, and here there are some real mysteries, that if we take as our multiplicative group zp star, then the discrete log can essentially be calculated, again, based on a heuristic algorithm, in the same time. This is not much safer than factorization. The C is a little bit different. Now, the similar thing, maybe you think, why didn't I talk about general fields? Let's say f2 to the n. The same kind of phenomenon. There is a fairly fast computation of the discrete log, and we are really unsure about where it stops and what may happen next. Now, for those groups, the discrete log, the best methods we know in general, in the general case, are take times square root of n. And are essentially the best thing that we can do is using what is called the birthday paradox to get some relation between group elements. The birthday paradox gives it, so-called, gives it in times square root of n, and that's our best knowledge. But however, there are strange things. For example, if the order of that was recently discovered by somebody very appropriately called, I think, Niles, but the last name is Smart. So if the order of the group happens to be p, also prime, the same prime that was used to generate the elliptic curve, then there is a fast algorithm. So we are really wading in a sea of ignorance. Now we come to Gromov's question. You see, these all depend very much on how that group is presented. So we have the notion, that's exactly your question. We have the notion of a cyclic group of order Q. That's unique algebraically. But if we use it as residues or same thing in a finite field, there is an additional structure which can be used. So we can use small primes here to form products and use smooth numbers and so on to get relations. And similarly, we can do in finite fields, say f2 to the n and others. This field, not field, I mean, this representation of the group doesn't have any discernible structure except for the multiplication itself. There are things which play a role here. There are Frobenius isomorphisms and so on, which may be used, but we don't know enough. We would be even safer if we had other clever ways of producing these cyclic groups. One bad way is, you would say, how about groups of matrices? They are about as bad a ZP. If we take, of course, we have to take them over a finite field because we can diagonalize them, and in most cases, unless we do something very clever, and then this is reduced by looking at the diagonal elements to the ordinary discrete log problem, maybe in a somewhat larger field, but there is more structure. So it's not easy at all to come up. However, this is in some sense the safest, and actually if we base cryptography on this, we can use, I don't have time to analyze, the analysis is fairly clear, fairly simple. We can use much shorter numbers than, let us say, in the x square mod n method. Because of this square root, our state of ignorance is its square root. So if P, for example, consists of, let us say, 192 bits, which can be stored in 3 computer worlds of the modern processors, the square root of that is already a number that would defeat any cryptanalysis method. And that's a great advantage because then the operations are much simpler. Now I want to very quickly talk about the question, when did I start? I don't look at this, I look at that.
Actually, now we have no limit. Right?
Oh, really? The people here don't have ripe tomatoes, but they'll find other things. I think we started at half?
Yeah.
Okay. Okay, so just talk twice as fast. So are there any hard problems? You see that those problems that we had before are somewhat dubious, except for the elliptic curve, except for say Al-Gamal encryption using elliptic curves. They are somewhat dubious because the algorithms are of a form that slight changes would greatly increase the range of encryptions that an adversary can break, would greatly increase. So maybe the idea is to go to the old trusted horse and go to the NP problems. So the question, are there any problems which are really hard? So the candidate is NP. And I give another example because first of all, that's how I did it in the beginning, and then Avi told me that he is doing free coloring, but this is more appropriate for me. So we have a formula which is in 3 conjunctive normal forms. You have Boolean variables, propositional if you wish, or 0-1 variables, x1 up to xn. You have a formula which has this form, a conjunction of oh, that's very nice. Yeah, that goes on. This was not written properly. So, yeah. Let me just spend a minute. So you have a conjunction of conjuncts like this. This is L11 or L13 and LK1 or LK3. So there are K conjuncts C1 up to Ck, each the disjunction of 3 so-called literals. I mean, that's really amusing what came out here. So this should, the last one should be K. That's the mistake here. The last one should be K. And each Lij is either a Boolean variable or its negation. So now the question of whether P is equal to NP is essentially, is there an algorithm, AL, constant C and D, such that for all M, meaning the number of variables for all M, and for all F of this form, but there are many formulas of that form, the algorithm produces a 1, says yes, if and only F is satisfiable. And the number of steps is polynomial, is C times M to the D. C and D are fixed. Now, here it's even clearer, because it is clear how Boolean formulas mimic Boolean circuits, and it is clear how Boolean circuits, that's actually what happens in computers, how Boolean circuits give you computations, and it is the only point that is not clear is that here we are asking a yes-no answer. So we are just asking whether that is satisfiable or not. How about finding a satisfying assignment? But the problem is self-reducible. If one of the people here finds a polynomial time algorithm, then actually the satisfying assignment can also be found. Because what you do, you say, well, okay, x1 is 0. So you substitute here, you get a reduced formula, you test whether it is satisfiable. If it is not, first of all, you test if the whole formula is satisfiable. If it isn't, you go home. We needn't look for a satisfying assignment. But if it turns out that for x equals 0, it is not satisfiable, therefore, the satisfying assignment must have x1, 1. So we don't get a tree explosion. Now we say x1 is 1. And now we have a formula with one fewer variable. We don't get to the point where we have to try all combinations. Consequently, if this is solvable, you can actually find a satisfying assignment. You can write, if you take the two factors p and q and write them by Boolean variables, you can reduce the fact that p times q is equal to n with a little bit of contortion to a formula of this form, and then you would be able to find the factors. I say that this would be very bad for a lot of theoretical cryptography. The question whether that is going to ruin actual cryptography will depend on D. Because if D is 15, say, if D here is 15, by 15, 212, just a random number, 212, then the fact that you have an algorithm which for 100 variables works in time 100 to the power 212 is not really very relevant. And therefore, if one looks at it seriously, and cryptography is very serious business, then one ought to compare it also to the other methods and see what they do. Now I want to share with you, even though this doesn't directly bear on cryptography, I want to share with you Gödel's insight. It is very, very difficult to make truly new discoveries, because it turns out that every important discovery, probably because it is important, almost every important discovery has antecedents. So for example, we know about special relativity. It's even controversial, Poincaré and other people, Lorentz. So Gödel wrote in 1955 a letter to von Neumann raising the following question or making the following observation. So I'm paraphrasing him to fit into what we are doing. And that's the question whether mathematics can be sort of mechanized in a sense stronger than Turing's. Essentially, we can pose the question as follows. First of all, we have to say what is mathematics. Now, I know that is going to be is controversial, but let us assume that it is everything which is deducible from say, Zermel or Frenkel axioms with the axiom of choice and whatever you want of set theory. We don't want to enter into philosophical discussion here. I doubt whether, say, any of us has proved a theorem which, even without doing it upon examination, could not be deduced from those axioms. So for our purposes, we fix the set of axioms, and we fix of non-logical axioms, and we fix the logical axioms, which we can take to be first-order functional calculus, because we can translate. I don't want to dwell on that. Now, this comes back to Avi's proof of the extended Riemann hypothesis. I mean, the man is really, I mean, if he already talks about proving Riemann hypothesis, not just Riemann hypothesis, extended Riemann hypothesis, which Alice, the postdoc, has and wants to, have the teacher examine. So the proof can be expressed in some reasonable way under translation. We know that everything is bits, can be expressed by a sequence of bits. And in fact, we take an annotated proof. This is a detail here, but we take a proof where you also have their comments saying the bits from 1 to 100 are some axiom, the bits and so on. It's a little bit more complicated. We have an annotated proof. And now we argue as follows. If we, mere mortals, would be able to prove a certain theorem, like if it is a theorem, the extended Riemann hypothesis, we wouldn't be able to have a proof which has more than, say, 5 million bits in it once we write it down. The language of logic is actually very succinct, and it doesn't have all this, it stands to reason by analogy and so on. It doesn't have the text. It's actually very succinct. So we can ask, and that was the question that Gödel asked, can we determine whether a certain statement has a proof of length n, say 5 million? So if this is a proof, we can write a formula which depends on the axioms and depends on including the axioms of logic and depends on the statement, which is about of length m squared, and that formula is satisfiable if and only p is a proof of length m, or at most m, we could have some nonsense at the end, from the axioms. Now, if p were equal to np or p were equal to rp, we could check that in time polynomial in n. Now, in fact, again, it depends what is the order of the polynomial. But Gödel said, what about if the time turns out to be m times log m? Now, even for 5 million, log m is not excessive, and the computer could do it. Even m squared would be would be feasible. Even m squared would be feasible. So I think that would have some meaning. So that was an aside. I just couldn't resist. And now I have to really run. I have to really run. I may come back to that. But you see, the fact, let us say that we prove that factorization, we cannot prove it's exponential. But let's say that we proved, we have no way of proving such a statement as of now. Absolutely no way. For most problems, Avi was too polite. Essentially, I think there isn't a problem, say, that we cannot prove, about which we can prove that it is not doable in linear time. So we can have a problem which is fairly obvious, which you can do in time, whatever, and you can't even prove that it takes 10n. So we are far, far away, and I think this ought to give us pause for thought. But suppose we prove that in the worst case, factorization is hard, say as hard as the Lenstra, Menasse's, the last name I think was Pomerantz. No? Pollard, yes, of course. The great name really in this area. So let us suppose we can prove that. This actually doesn't help us. You can amuse yourself or maybe spoil your own dinner by trying to prove the following: that if P and Q are numbers in n equals PQ, if P and Q are numbers such that P minus 1 and Q minus 1 have only small factors, then actually, in fact, it's enough if p minus 1 has only small factors. Then actually you can factor n. So an additional note of caution. Now, of course, these numbers are rare. Whereas we have shown that the x square mod n, if n cannot be factored, is safe for almost all messages, overwhelming number of messages. It could be that for the overwhelming number of keys n, we can factor. So it is not enough to just show that factorization or discrete log is hard in the worst case. For secure cryptography, we must find a subclass where we can show that it is hard on the average for all of those cases. Otherwise, we are not safe. We essentially have almost no way of tackling such a problem. So let me just mention the following. Let me mention, and one good reason for mentioning it is because Lovash is sitting here. Let's mention the shortest vector in lattices. So very quickly, we have vectors. They could be taken over the reals, but there are questions of representation. We have vectors in z to the n. So we have n vectors in z to the n. They span a lattice. And then we can talk in the lattice in this lattice, we can talk about the shortest vector, the second shortest vector, and so on. Now, first of all, an extremely important algorithm of Lenstra, and Lovash showed that in polynomial time you can find a vector which approximates the shortest vector by a factor of 2 to the n over 2. Even though this is extremely generous, 2 to the n over 2, it turns out it has far-reaching applications. For example, the factorization of polynomials with rational coefficients. Now, is there a hard problem hiding here? Yes. This wasn't easy, but let me only mention the first one. Finding the shortest vector is NP hard. We don't even know that it is an NP. In other words, if we have the shortest vector, there are some people, you know, when the truth hits them in the face, they don't recognize it. But here, certainly, a shortest vector can hit you in the face, and you won't be able to recognize it. But finding shortest vector, maybe even recognizing shortest vector, is NP hard. Neither can you approximate it, but that's a weak result. Now, ITI has constructed, don't read this. I mean, it's too late for this. ITI has constructed a class of lattices which has the problem that if you can solve the shortest vector problem in those lattices for the average one in polynomial time, then you can approximate the shortest vector in an arbitrary lattice within a factor he proved n to the 11th has been improved to n to the 5th. So we have a class. We don't know, however, whether that approximation is hard or not. We only know that finding the shortest or approximating it by a factor of square root of 2 is hard. We don't know about n to the 5th, and from the point of view of the cryptographers, it's a very embarrassing fact that one has to understand that statement properly, but actually the L cubed Lenstra-Lovash algorithm is even much more efficient and actually gives very often an approximation within a factor of 10 in cases where we can recognize the shortest vector and so on. So we don't know whether he has a reduction to a really hard problem. He was able to base on his problem a construction of something that Avi alluded to, of a one-way function, a basic building block in cryptography, and then you can also have, on a slightly different assumption, Dvork, and he constructed also an inefficient but an encryption, except that we don't know whether the problems they are talking about are really NP hard or not. So now I'm going to discuss some of the additional dangers in cryptography. And the first business is malleability. This is not just the business of keeping the M secret. Suppose you have an adversary which doesn't just listen, but is active. And he captures this method, he cuts the line, he captures the method, the message, the ciphertext, and suppose he has a function which he can apply to Y, a computable function. He gets a Z, and he sends Z to the receiver, who when he deciphers gets a function known to the adversary of M. Now this is not that impossible. Consider the function that we first had. Consider the function that we first had. In case that it is possible, we say that, that we have malleability. Consider this function. So in this function, it is clear that if the adversary captures the ciphertext, he can replace the thing in there, he can replace M by 2M, simply by multiplying the ciphertext by 4. And then the 4, mod N. The 4 is the same as the encryption of 2M. And that may be a tool in his hands, depending upon what's going on. It may be a tool in his hands to cause some damage. I give the example, nobody knows if this is possible or not, where this is replaced by M minus 100. So if there is bidding, so somebody can take somebody else's bid, and without knowing what it is, because the bids are sent in an encryption form, maybe do something to the ciphertext, replace the insides by M minus 100 and beat him in the bid by a small amount. So, okay, it's clear. No, in the bid it should be M plus 100. Okay, doesn't matter. So he is slightly above him and wins. Now, most of the encryptions which we had before are clearly malleable. Now, there was a construction, a specialized construction for a special function which creates non-malleability. Jonathan Aumann and I found a method so that for every encryption scheme, we can enhance it so using this encryption, but encrypting the message several times and doing various things to it, so that provably now the encryption is non-malleable. And the point is that this is also a relatively efficient construction, and we can achieve this non-malleability. And this is a problem which is not just solved by, say, hardness of p-time, factorization. So that's malleability. Now, chosen ciphertext attacks. Consider this picture here. Consider this picture here. And by the way, it was on the slide. I should mention it. I skipped. So the concept of non-malleable encryption was introduced by Dwork, Dolev, and Naor in '92. They had a construction which involved extremely complicated zero-knowledge proofs of a certain kind, non-interactive zero-knowledge proofs, and that renders the whole method completely impractical. So the point here is that there is a practical solution. Now, chosen ciphertext attacks. So consider this scheme here. So another thing to be paranoid about. An adversary captures the ciphertext, doesn't change it. Just it goes through, but he listens. Let's say he cannot interfere. he captures the ciphertext attack. Now Bob has a decryption box, so-called, which uses his private key, for example, the P and Q. Suppose we did encryption, which is, are you going to drop me into the, huh? In 5 minutes, okay. Maybe I'll talk until half. No? Okay. So he captures it, and now suppose he can submit other messages to the decryption box, but not this particular message, and use what he got from the decryption box. Maybe he has access. Maybe he can break into Bob's computer and use the decryption box. And thereby also gain information about M. Now, I cannot show you the solution, but there is an algorithm which again enhances the encryption. Any encryption is being enhanced into a form that allows a proof of plaintext knowledge. When the box gets this ciphertext, and this looks almost miraculous, Alice proves that she knows M without revealing anything, without using zero-knowledge proofs in the classical sense, which are highly inefficient. And now, of course, if she proves she knows M anyway, then the chosen ciphertext attacks become useless. Because after she passed the exam, by the way, it's also quite remarkable that the examination is done in the clear. So no encryption is used during the examination. And this is given in this box, and I understand that we don't want to know about it. So two more things. One is deniable authentication. So it is very important, this message goes in the clear. It is very important to have protocols for authenticating the message. We know that when we log into our computer, we authenticate ourselves by a password. A very bad method, because if somebody captures the password, then he knows everything. So there are more clever ways, which are essentially short zero-knowledge proofs for authentication. But that's for the person. Now suppose Alice logged onto the computer, and now she's sending sending commands to the computer, like send email to somebody and so on. But after she logged in, somebody cuts the line and sends instead of her all sorts of commands. So actually there is a need for authenticating every message. So there are message authentication protocols, which are also of the utmost importance. But why do we want to talk about deniable authentication? We want to create a protocol whereby, and that sounds almost completely impossible, Alice, the sender, sends a message M and proves to R that she is actually the author of M. However, let us say that this is in electronic voting. The message can be in the clear. This is in electronic voting. And the regime is not quite democratic. There are inquisitors there, or people who may become dictators later, who go and try to get from R how M voted. It is possible for S in a simple way. I wish I had the time to show you how to solve this logical puzzle, to prove to R that she, S, is the author of the message M, but in a way that even if I listen to the whole conversation and then goes to R and goes to S and asks them for all the private keys and everything, S will still be able to deny that she is the author of the message. So the loss is yours. I won't be able to show you how that is being done.
I will ask this question from the start.
Okay, good. Okay, so I'll start. I'll start. I'll start preparing myself. So now we want to talk about everlasting secrecy, and I mean everlasting secrecy. We know already that keys are not safe, and we know that the safety or the efficacy of the key depends on the march of technology. And this is independent of whether P is equal to NP, unless we prove unbelievably strong theorems about some encryption method. Pointed, average case, exponential, and so on results. So if this was sent encrypted, say, by a 1,000-bit RSA key, or in my method, the X square mod N key. And then, in a year from now, somebody factors numbers with 1,000. We saw that an improvement, removing the constant from 2 to 1 has an enormous impact. Then the listener on the line records all this conversation, keeps it. By the way, secret services do it, so that there are messages between spies, Russian spies. There were such. In the United States, messages between spies to Moscow, which were kept and which were decoded 15 or 20 years later. So that won't do. So it is clear that the only way of achieving everlasting secrecy is if the adversary cannot store the whole conversation. So the method which was proposed by Maurer, but the main theorem was proved by Aumann and myself, consists of the following. Here you have a string of bits, say 10 gigabits, 10 billion bits. It's possible to send such strings. The adversary is limited in storage by, say, 5 gigabits. The sender and receiver have established, by means of a public key, which may be broken 2 hours later, have established a private key. And they are listening to chosen locations. So they know where to listen. They wait to I1, they listen then to M, if the message is M length. And then they wait until I2 and listen to M. And I1 up to IK is a secret key that they have. K is, say, 200. Not very large. The poor adversary can listen only to a fraction. And he doesn't know what to listen to while this is happening. And then you can prove an information. Now, out of that, you can make a code. Because essentially, you take the XOR group, you take the XOR of these bits, you take the XOR of those bits which they listen to, they take the XOR of these bits which they listen to, and they make a so-called one-time pad which they use to encrypt the message. So forget about the details. These are standard methods. So the theorem that we had is the following. He considered, Maurer and then Kachin and Maurer considered the limit storage model where essentially they can only store the original bits. And then they had another version of it which, however, gave very low security, 10 to the minus 4 security, which is not sufficient. We have proved the following. If the adversary can compute any function of all the bits that he listens to. So first of all, he can on the fly compute any function. It doesn't even have to do with computability, any fixed functions. But then he can store only n over m bits, where m is the length of the message. then this is safe in the following strong sense. Even if the secret key becomes known to the adversary, and even if he knows that the message is one of two messages, sell IBM, buy IBM, promote associate professor so-and-so, or fire him. Yes, and they are afraid that associate professor so-and-so will join the NSA and all this, etc. Even if that is the case, the probability of distinguishing between these two messages, so M delta is one of the two. Delta is either 0 or 1. To compute which one it is, to distinguish. Of course, he can always guess. So that gives him probability 1/2. But the probability is smaller than 1/2 plus 1 over essentially 2 to the k. But of course, if he could make a mistake, which is very big, then he would shift around. So the significant statement is that the probability is bigger than 1/2 minus that. In other words, it's very close to 1/2, exponentially close. K is the size of the key that was used. So the key in this case, so that is going to be at long last, it's everlasting security, and that is going to be the last slide. The key that they share is I1 up to IK, which gives you the location in here in the very long string that they will read. And K can be small, like 200. And you get security which is exponential in, 1 over 2 to the k. I mean, we had k over 5. We can improve it. And that, regardless of what will happen to p equals np and to factorization and so on, regardless of that, if we have some assurance that the public key cannot be broken before the protocol ends, that's enough. That's enough. Now, this is not that far-fetched, and the only, and here there is a problem. There are lots of problems, of course, but the fly in the ointment is that here we say, let's say, n over m bits. We suspect it's true also for n over 2 or 3, so that it does not depend on m, some variant of that. The method of proof, the last word, the method of proof, it also uses a form of discrete Fourier analysis, but more refined, related, but more refined than the one that Avi alluded to. And of course, we assume that the string alpha is random, but the way that we like to look at it is to say that the string alpha is of maximum Kolmogorov complexity, is incompressible in the sense of Kolmogorov. Then we have, I mean, it's really just another aspect of counting, but we have the and of course, almost all random strings have Kolmogorov complexity maximum, which is n, or say n minus 10. So, and then for this individual string, the theorem holds. And that's the end of my story. Thank you.